uncooled mirror imaging sensor technology and applications.
Okay, good morning. I would like to thank to Pascual for inviting me to be here. I have to recognize that the first time that Pascual called me, okay, I am not a guy of photonics integrated circuit. I am a guy who has been working all his life in infrared sensor, but not in photonics integrated circuit. I prepared this presentation. I hope this presentation will be interesting for you, but I am speaking about infrared sensor overall. I hope you find this presentation interesting for you. My name is Germán Vergara. I am the Chief Technology Officer of New Infrared Technology, which is a small company located in Madrid. We are 9 people, and we are running since 2008 our own infrared technology, and we develop sensor, cameras, and system based on it. Okay. Okay, all of you are working in photonics, and it means you have an idea of what is infrared, what is uncooled, what is the imaging. And maybe many of you are working, thinking about what is new with these people is telling us. Okay, I can tell you that what is new is to put together all these concepts, medium wave infrared, imaging, and uncooled. This is new, and my talk is prepare or focus in explaining you why it is new. Okay, let me to start giving you basic concepts of infrared detection. An infrared detector basically is a device which converts infrared photons in some magnitude, physical magnitude that you can measure. But I'm not here to speak in general in infrared sensor. I'm here for speaking about a specific type of infrared sensor. I'm here to speak about solid state infrared sensor. It means that the device is a piece of matter which is solid state matter. Fortunately, this type of sensor are the most interesting type of infrared sensor from the technological and from the application point of view. It is very important because it means that behind physics of sensing, you can follow the rules of the interaction between radiation and matter. This is very important that you understand it. Okay? Following that, here you can find, maybe many of you have seen this type of charts. This is a very famous chart. You can find the most interesting infrared sensor in the market. In the y-axis, you can find the detectivity. Detectivity is a figure of merit that it takes in account the signal to noise ratio and gives you an idea of what is the sensitivity of the sensor. In the x-axis, you can find the wavelength of the photons. And the first thing I would like to mention is this yellow curve. This is like an upper limit of the detectivity of the sensor, but it is not due to the device itself. It is due to the world where we live. We are living in the Earth, and the average temperatures in the Earth are around 300 kelvins, and everything is emitting photons. It means that we are living inside, immersed in a sea of photons, and it means that this sea of photons we call background, and it means that even in case you have an ideal sensor with quantum efficiency of 1, or you have a detector with no noise, you are limited by the background. This is basically that this curve is telling us. The other thing I would like to tell you is, all of you know that we are living in the Earth. There are some atmosphere, some gases, and the gases are not transparent to all wavelengths. And this means that we divided the infrared more or less in 4 main bands: the short wave, the medium wave 1 to 3 to 5, 1 to 3, and long wave infrared 8 to 12. Beyond, you can have very long wave infrared. This is something that every people knows here. Okay. But if you pay attention to this chart, you will find like two different types of sensor. In the bottom part, you can see here some sensor that the detectivity or the sensitivity is constant in a wide spectral range. These are that we call thermal sensor. Thermal sensor, as the mechanism is described here. The photons is arriving. They are absorbed by vibrational and rotational state of the molecules, and due to the agitation, they heat up, and some characteristics or some parameters of the solid state matter change with the change of temperature. Taking account it, I have some remarks to do. The first remark is a four-step process. You have to take into account that each process, the efficiency is less than 1. It means that the total efficiency is the product of all, and that is the reason because they are in the lower part of the chart. Of course, they depend on change of temperature, and change of temperature used to have an inertia, thermal inertia, and they used to be a slow sensor. Another important thing is the spectral response is constant, because they all just depend on this one. And also an important thing is the light absorption is related with molecular vibration and rotation. It means you don't need too much order in the device, in the solid state structure. It's possible that you can obtain good thermal sensor in amorphous materials. It's possible to do that. And the other characteristic is that they don't have a very low dependence on the working temperature of the sensor. They are working with it's a differential work in different temperature. The other type of sensor are in the upper part of the chart. These are that we call quantum. I don't know why to say quantum, because all are quantum, but in any case, they are called quantum. These are the mechanism, and as you can see, the photons arrive, then they absorb, and this absorption, this energy is absorbed. Basically, they promote electron interband of sensor, and due to that, it changed some parameters of that I can measure. The first thing you can see here is three-step process. One step less than the thermal sensor. It means they used to be more sensitive. They are really fast sensor. They don't depend on any change of temperature, which is also interesting for some application. The response is not constant. It depends on the band gap. The other has a cutoff. Another very important thing from the technological point of view, they need some type of order in the solid state structure. This is very important. I will mention later, but this is very important thing. Finally, they have a severe dependence of the working temperature. This is due to when we are moving to longer wavelength, this distance is going smaller and smaller, and start to be important the thermal generation of carriers, and then it is basically a noise. But let me give you more information about the working temperature, because it's important for all this history. Okay, you can see here in the red curves are the uncooled sensor. They're working with any type of cooling. And you can see here how the detectivity is dramatically decreased with the wavelength. Okay, this is due to the thermal generation problem. Then you need to go further, you need to cool down, and I divided this in that we call hot sensor. Hot is high operating temperature sensor, that They used to operate at minus 100, minus 150 degrees. And finally, you can find the cryogenic sensor that they need very low temperatures, nitrogen, liquid nitrogen or helium nitrogen, etc. I divide in this because basically the hot can be cooled by thermoelectric cooler, and the cryogenic and helium, they need a cryostat or a Stirling, etc. But the most important drawback of this is this one, the cost, and also another important drawback of this sensor is the reliability of the sensor. It depends on the cryostat more than the sensor. It takes a lifetime limited. Okay, then Christmas was like 3 weeks ago, and if I have to write down letter to the Magician Kings or to in my wish list, if I have the possibility to use and cool sensor. This is basically the message that I will try to send you. Okay, I'm going to because as I told you, I'm going to speak about imaging, and let me to start with imaging. The imaging refers to the ability to capturing, storing, and displaying image. For doing that, I have 3 different types of solutions. You can see here, I can use a point detector, and then to move the detector in 2 dimensions, X, Y. I can use a line and just only scan in one direction, or I can use a matrix of M by M sensor. This is that we call a starting sensor. The 2 first solution has 2 main drawbacks, inconvenience. Both of them need movement, and then you have to apply some type of movement or scanning mechanism for reconstruction the scenario. But the very important drawback is the integration times are very short. You have to divide the integration time of the detector by the number of pixels that you are scanning. And this is a complete disaster when you are trying to use for frame rates, etc. Then again, if I have to write my wishing list, I would prefer to use M by M sensors or a Stalin sensor. This is basically, but studying imaging requires technology. This requires an array of sensors that we call focal plane array, and the focal plane array manufacturer requires the technological capability of processing solid-state device with M by M pixel in a sensitive material, integrated all in the same piece. This is a real technological challenge. Don't forget, you have to move. You have to process this one and this one in the same. It means that an infrared focal plane array requires the merge of 2 technologies: the infrared material technology and the readout circuitry technology. Okay, this is what I'm trying to say in this slide. The only thing we can do is to put in the SY-X the infrared material, and in the 3rd dimension the readout circuitry. Okay, this is basically the standard architecture that we use. And in case of array, the only thing you have to think that the size of the pixel has to be small and small, and we need to use integrated circuit for making everything more and more small. And the only thing that we know to do is to make integrated circuit in CMOS technology, which is basically the way. It means that CMOS is a common technology to all FPAs. This is something that I would like to send you the message not all the CMOS cameras have CMOS. All cameras have CMOS. I mean, when I've been telling you CMOS cameras, visible cameras that you use in your phones and so on, no. All cameras, independent of infrared, UV, etc., all has CMOS circuitry behind. Okay. Okay, and then we have to make the integration of all these technologies. The technology 1, the infrared material, and technology 2, the CMOS technology. And in this case, we have two options. The first option is what happens if the technology of the infrared material is not compatible with CMOS material. I cannot process at the same, in the same substrate everything. And in this case, that we do is to make what we call a hybrid device of hybridization. It means that we use some, we use some Indian bumps, and we process the array of irresensitive material by one side, the array CMOS by the other side, and we put together in a hybridization process. In case of the most quantum sensors, they used to be high quality crystalline lattice. And it means that they will require some high temperatures and so on, and most of them are hybrid sensors. Monolithic integration. Monolithic integration is the capability of processing everything on the same substrate. Okay, and again, in my wishes list, I will prefer this one. It's much easier and it's cheaper, and I can obtain more integration. But this is, unfortunately, is very infrequently. It is not possible to find it. Okay, we are now close to be what is new. But, okay, this is the panorama of the infrared imaging 10 years ago. 10 years ago, you can find good cameras of in-gas sensor in the shortwave infrared. They are quantum sensor, and they are hybrid technology. It was possible to find very good cameras in the long wave infrared. They are microbarometers, they are thermal sensors, and they are monolithic. It's a monolithic technology, but there was not any type of medium wave infrared imaging in uncooled operation. The reason because this is here. MWIR is a very attractive band. You can do a lot of things there, gas detection, thermal imaging, spectroscopy, industry, and so on. The reason why MWIR and cool imagers were not available 10 years ago were mainly technological. Few uncooled MWIR detector available. This one. The thermal sensor have a limited sensitivity here, and also they have a very slowest speed, and they have some technological issues. I'm not going to go into that. And the quantum sensor have higher sensitivities, and they are fast. However, they will require to grow crystalline lattice, which is synonymous of complex and expensive technology, including hybridization. It means that you have to spend a lot of money for making a device with a performance cost ratio very limited. And that is the reason because 10 years ago there was not any type of medium wave infrared sensor. But sometimes the technological advance are able to turn obsolete in an emerging technology again. And this is we are now close to know what is new. What is new is this one. The old, unforgotten, and tricky. Tricky is because they are polycrystallines. Lead salts are initial quantum sensors. You remember, they have an acceptable sensitivity in a cool operation. And if you remember when I told you they demand long order material. This long is a flexible concept. It means that opposite to the majority of the quantum sensors made of high quality crystalline lattice, LITSAL are disordered materials made of compact layers of polycrystal. It's a polycrystalline material. And this polycrystalline nature has some disadvantage because it's really tricky to make that, but they have very good characteristics for the integration with CMOS. They have a simple and low-cost depositing technology. They have very low temperatures necessary during sensor processing. They are compatible with substrates. We don't have to worry about no longer with thermal mismatch and nothing of this. This is a polycrystalline material. And they adapt all the thermal matching and so on. And the solution to this was in the polycrystalline world here. The monolithic integration of lead selenide sensor with silicon CMOS was possible and demonstrated in 2008. It was demonstrated the first device. This is new. The development of a new way of processing lead selenide fully compatible with silicon CMOS technology is called vapor phase deposited lead selenide. This is the technology that NIT is running now, and we have some records right now. The record is the first quantum infrared sensor monolithically integrated with silicon CMOS. The direct and simple disposition on 200 millimeters silicon CMOS wafer. You can see here one of them. It was developed with the help of the Centro Nacional de Microelectrónica of Barcelona, who has been made excellent work in developing redout integrated circuit for this sensor. At present time, New Infrared Technology is the unique company in the world able to process and cool MWIR cameras, and now is the fastest and cool infrared imaging in the market. All this record has this technology. You can see here the tip hot chip solver obtained with the Tachyon 16K, which is one of our imager. And I have all these things in the wishing list. It's uncool, it's MWIR, it's starting, it's monolithic. Okay. These are the history. In 2008, vapor phase deposited became the first and still unique infrared quantum technology monolithically integrated with silicon CMOS. In 2010, New Infrared Technology launched the first commercial device. In 2014, it launched the first Tachyon family device. It was a 32 by 32 pixel, 10,000 frames per second, which is a lot for infrared. And a global shutter, which is also very important for some application. In the medium wave, in this year, we have just launched the 128 by 128, which is this camera here, 2,000 frames per second, and it's interlated. And this year, we will launch the new version of Tachyon with a global shutter, with 4,000 frames per second, which is a lot of velocity for something. Okay, just let me speak a few words about application. Maybe the most important application for us right now is the industry. The industry is now using laser for everything, for additive manufacturing, cutting, welding, surface texturing, etc. And the processes with laser are very fast process, and they need to be controlled in real time because they demand real-time controlling and monitoring. And high-speed infrared imager also available tools for monitoring and controlling in real time. The big advantages are this one. This is the melt pool provided by a CMOS camera. This is the melt pool provided by the MWIR camera. You can find much more details of the melt pool. These are some products that we have based on our technology, and I think this year we won the Innovation Radar Prize in 2018 with this product in the European Commission. It was a Clamir product, which is possible to control in real time additive manufacturing process. Okay, this is another very interesting application of our sensor. This is a really, it's a wonderful project. It's called MWIR project, and we are trying to put a face to a gas. Basically, that we are trying is we use a supercontinuum laser source, and we divided the spectra in two dimensions, not in just one dimension. And this that we are trying to is to identify gases in two-dimensional plane. And this is the spectra of N2 oxide of nitrogen, but it is made with uncooled cameras. Finally, we don't have any application in photonics integrated, but I think it is still the technology is still the unique quantum sensor monolithically integrated with silicon CMOS technology. It's a simple technology. We can get large-scale integration. It's compatible with silicon photonics, which is now many people working on, and sensitive in a wide spectral range up to 5 microns, which could be interesting for many of you. It's suitable for a sensor in the MWIR integrated photonics platform for this potential application. And that's all.
Thank you, Germán, for your talk. Are there any questions from the audience? Okay, so Germán, could you tell us this kind of sensors, which countries, for example, or from which applications more in deep are sold for these kind of cameras?
Right now, our main application is laser processing, which is, okay, this sensor has a clear defense application. In principle, the technology was born in the defense laboratories. But I cannot speak about them. But from the industrial side, we are now very concentrated in laser processing and also in gas detection.
Thank you very much, Germán.
Hi, thank you. Thank you very much for the talk. I have a question regarding the application of your infrared camera. We are in Indra, we are using this kind of sensors for detecting drones in the air and also for spill detection on the water. Did you thought about use this camera in this kind of applications? Another question, did you work with Indra also before?
Yeah, we have. We know Indra very well. Okay, you have to think that this is an uncooled camera in the medium wave infrared. It means you see the detectivity chart, you will see that we are in the lower part. Now, our detectivity is limited compared to the cool detector. In the application that you mentioned, probably in case of detecting drones, it's better to go to thermal cameras because they are more sensitive to lower temperatures. And for spill and so on, it depends on the reflection, the wavelength of the reflection, but it is possible that we have never tried that. But for instance, it's very useful for detection spills in gas and oil because they use medium wave infrared. There is a big absorption in 3.4 microns, but not in the reflection of in the sea of different type of materials. But I mean, we can try.
Are there any more questions?
Hello, I have a question just for the application of the detection of micro cracks in laser wells. Is this type of camera detecting cracks in just metal wells or glass wells or any other particular material?
Okay, just let me to try to explain what we do. Basically, that we do is we have two ways of operating: on axis and off axis. On axis, it means that you are always watching the melt pool, and if the melt pool, the cracks are formed in the cooling during cooling the melt pool. If you have a field of view enough and you can see the cooling, it is possible to detect cracks. If you want to work off axis, it's easier to do that. But it depends again of when the cracks, because sometimes the cracks are formed like 1 day later. That is something that, but trying to answer your question, yes, we can detect cracks, but it has to case by case. It's not an easy